Hey everyone, and welcome! Today, we're diving deep into the world of engineering mechanics. Now that might sound complicated, but it's really the invisible science that's holding pretty much everything together, from the chair you're sitting on to the tallest skyscrapers on Earth. So, let's get into it.
So, take a look at this crane. We all know its job is to lift these insanely heavy containers, but here's the real secret, the thing that's arguably more important, its ability to just stand there, to hold all that weight perfectly still without buckling. You see, the magic of engineering isn't just about making things move, it's about figuring out how to make them not move. And that, right there, is what we're talking about today.
And yeah, there's a name for this science of standing perfectly still. It's called statics. It is all about objects that are at rest and all the forces acting on them are in perfect balance. Think of it like the art of achieving perfect equilibrium, just on a massive structural scale. Honestly, this is the foundation that almost all other engineering is built on. Okay, so to really get a handle on statics, we first need a map, right? We need to see where it fits into the whole big, wide world of engineering mechanics.
Check this out. This is basically the family tree of mechanics. You can see up top the whole field splits into three main kids. Rigid bodies, that's things that we assume don't bend or stretch. Then you have deformable bodies, which, you guessed it, they do. And finally, fluids. We're going to follow that rigid bodies branch, and that branch splits again into statics, our focus, the study of things at rest, and dynamics, which is the study of things in motion.
And that's us. That's our stop for this explainer, right here in statics. It's all about these rigid bodies that are in equilibrium. And that just means all the pushes and pulls acting on them perfectly cancel each other out, so they stay put.
You know, when you boil it all down, this is what mechanics is all about. You've got a body, and that could be anything, a tiny screw, a car engine, a massive bridge, and then you've got forces pushing and pulling on it. Mechanics is simply the science of figuring out what happens next. Will it move? Will it bend? Will it break? Or will it stay perfectly still?
All right, we've got our map, we know where we are. Now it's time to build our toolkit. Because before you can solve any engineering problem, we all have to agree on how we're going to measure things. We need a common language.
And believe it or not, everything in mechanics, I mean everything, is built on just four fundamental ideas: length, mass, time, and force. And what's so cool is that they're all connected, all tied together by one of the most famous equations in all of physics, Newton's second law, force equals mass times acceleration. This little equation, it's the glue that holds our entire toolkit together.
Now here's where it gets a little interesting. When it comes to actually measuring this stuff, engineers basically speak two different languages or use two different systems. You've got the International System, or SI, which is pretty much the standard everywhere else in the world. And then you have the US Customary System, which, well, is mainly used in the United States.
And here's the key difference. You really got to get this. In the SI system, the base units are for length, time, and mass. The unit for force, the Newton, is actually derived from those three. But in the US system, they flipped it. The base units are for length, time, and force, the pound. And the unit for mass, which has the wonderfully weird name slug, is the one that's derived. It's a fundamental difference in how we think about the world, and it's super important to keep straight.
And this visual really drives that point home. See on the left? In the SI world, a 1 kilogram mass feels a gravitational pull of 9.81 newtons. But on the right, in the US system, a 1 slug mass, which is way heavier by the way, feels a gravitational pull of 32.2 pounds. It's just two different ways of talking about the very same thing.
Okay, so that leads to the obvious question, right? If you're an engineer working on a project with parts from all over the world, you have to be bilingual. How do you translate between these two languages? How do you turn pounds into newtons, or slugs into kilograms?
Well, you use a translation guide, or what we call conversion factors. This table is your new best friend. It shows you the most important ones you'll need to know. For example, 1 pound of force is the same as about 4.45 newtons. Keep this chart handy, because using these is absolutely crucial.
So, we've got our map, we've got our toolkit. Now, we need the instruction manual. We need the rules of the road that make sure we use these tools the right way with absolute precision.
These are pretty much the non-negotiable golden rules of engineering math. First up, dimensional homogeneity. It's a fancy term for a simple idea. You can't add apples and oranges. Your units have to match up. Second, significant figures. This is all about being honest with your numbers. Don't pretend your answer is more precise than it really is.
As a rule of thumb, we use at least 4 sig figs while we're doing the math, but we only report the final answer with 3. And finally, standard rounding rules. Nothing fancy, just keeps us all on the same page.
Oh, and here's a little pro tip that'll make your life way easier, especially in the SI system. It has these awesome prefixes to handle big numbers. So instead of writing out 1,000 newtons, an engineer just writes 1 kilonewton, or Kn. It's cleaner, it's simpler, and it helps you avoid silly mistakes.
So we have the concepts, the units, and the rules. Now let's put it all together with a really powerful 3-step master plan that engineers use every single day to solve problems.
It's called the IPE method: interpret, plan, and execute. It's so simple, but so effective. First, you interpret. You actually read the problem. You figure out what information you have and what exactly you need to find. Second, you plan. You make a roadmap. What are the steps? What equations do I need? And finally, you execute. You do the math, draw your diagrams, and, this is the most important part, you check your work.
All right, time for a little pop quiz. Let's put this all to the test. You've done your calculations, and your calculator spits out this number, 12,345.6 newtons. So, based on the rules we just talked about, how should you write your final answer?
And the answer is 12.3 kilonewtons. Did you get it? Here's why. First, we round to 3 significant figures. That takes 12,345.6 down to 12,300. Then, to make it clean and easy to read, we use that kilo prefix. So, 12,300 newtons becomes 12.3 kilonewtons. That's a perfect engineering answer.
And really, this brings us to the biggest takeaway of all. Engineering isn't just about getting the right number. It's about communicating that number with the right precision. Getting the answer is only half the job. Presenting it correctly with the right units and the right level of confidence, that is what turns a simple calculation into a piece of reliable engineering. And that, my friends, is the foundation for building a world that doesn't fall down.